So, I have been discussing on properties of polymers, and I have started discussion on thermal, mechanical and viscoelastic properties. In this lecture, I will focus mainly on thermal properties and on amorphous state. As I was discussing at the end of the last lecture, that thermal properties of polymers are very important for processing as well as product performance, and the mechanical and rheological or viscoelastic properties of polymers are also well related with the thermal properties, as I will discuss in coming lectures. Again, as we have discussed, amorphous polymers, they are entangled frozen mass with practically no order, and these polymer are characterized by a glass transition temperature. Similarly, for a semi-crystalline polymer, we have both amorphous domain and crystalline domain, which corresponds to Tg and Tm, glass transition temperature and melting temperature. So, we have been talking about this glass transition temperature and melting temperature. These are the typical thermal transitions in polymer sample. Now, if we think about a liquid, say like water, and decrease their temperature, what happens? When the temperature is decreased, it becomes more viscous and it flows less freely. Now, when the temperature is sufficiently low, then small molecules like water or other small molecules, simple molecules, they crystallize at a particular temperature quickly, form a solid crystalline material, and that temperature is called melting temperature, as we all know that. But if the sample or the molecules present in this liquid state are large, quite large, like large polymer molecule, and in complex shape, then it is very difficult for this molecule to undergo translational and conformational reorganization to pack in a crystal like manner. Like when you form a crystal, then it has to come and align themselves in a particular order. Now, if the polymers are very large, then they are all entangled with each other in liquid state. So, when you decrease the temperature sufficiently, then also it is not possible for the polymer molecules to undergo translational and conformational reorganization to fit into a crystal lattice. Now, if that happens in some cases, and also if the structure of the polymers is so irregular that this crystallization structure cannot be formed. And if the polymer is not able to crystallize, then if the temperature is reduced further and it goes below a certain temperature, it becomes rubbery in nature, and if you reduce the temperature further, then the viscosity of the liquid becomes so high that it is like a solid material. It does not flow at all, it is becomes very hard and polymer glass material. So, it does not have a regular arrangement of like a crystal structure, but it is viscosity is so high that there is no mobility of the molecules and is almost like a solid material. And in this case, the conformational changes associated with the normal volume contraction or crystallization now no longer take place in the glassy state, because there is no freedom at all. So, the conformational changes associated and volume contraction because of decrease in temperature further does not happen. So, the thermal coefficient of expansion of this material, glassy material, falls to about 1/3 of the value in a warmer liquid condition, because it cannot the molecules are large and they are almost like a frozen state, they do not have any mobility. So, it cannot contract during decrease in temperature. So, the coefficient of thermal expansion for these glassy materials falls about 1/3 of its value compared to warmer liquid condition. So, if we graphically represent the volume versus temperature curve, if we start from a molten state and decrease temperature, the volume decreases, and if the material can pack well, crystallize, then volume suddenly drops and a solid state is formed at melting point or melting temperature, and when we decrease further, the volume change is negligibly small because it is in a solid state now. But as we said, if the molecules are large, like large polymer molecule, then they do not have enough flexibility or enough freedom to rearrange themselves and pack in a crystal matrix. Hence, it will continue to, without crystallizing, it will continue to decrease its volume, and as temperature will come, in fact, a range of temperature will come when it cannot contract further, because practically there is no mobility, viscosity is extremely high like a solid, and this particular temperature is called glass transition temperature, and below which there is not much contraction. Now, as you can imagine, if we cool it at different rate, then this temperature glass transition will vary little bit, because if we cool faster, then you are giving less time to polymer to rearrange and pack, or basically access different or become compact. Whereas, if you give you more time, then polymers still have some time to basically orient themselves or change the conformation and further compact. Hence, if we generally do cooling faster, then we get a higher Tg value compared to a cooling where we are doing a much slower rate. There we generally get a lower Tg. So, for 100% crystalline, we get a Tm glass transition temperature. For amorphous 100% amorphous, we get a glass transition temperature, but unlike the melting point or melting temperature, glass transition temperature actually varies depending upon different heating or different cooling rate, because this determine or the time a polymer molecule can get to reorganize themselves and compact or expand. The temperature at which the polymer undergoes this transformation from a rubber to glass is called glass transition temperature or Tg. We will discuss more about this Tg and see what is actually happening in terms of molecules. Now, in case of a semi-crystalline material which have both amorphous phase and a crystalline phase, in that case if we decrease the temperature, then part of the polymers will actually crystallize, and because there are amorphous region or regions which are not crystallized, then this change will not be as sharp for a 100% crystalline small molecule. So, there will be a range of temperature during which this crystallization or part, some of the polymer molecules will crystalline, and we call again like melting temperature, but in this case, unlike this case, there will be a range of temperature where these polymers will crystallize, and it will continue after that till we reach glass transitions temperature, below which the contraction becomes much lower compared to the state IR. So, this is a purely 100% amorphous material and this is a semi crystalline material which has partly crystalline domain and partly amorphous domain. So, this is for semi crystalline. So, crystallization polymers do not crystallize completely as we discussed earlier. It crystallize or melt over a range of temperature as I just discussed, especially if there are high molecular weights. The temperature at which polymer undergoes crystallization and cooling, that is called melting temperature, Tm. So, now we know what is Tg or glass transition temperature for a polymer and a melting temperature or Tm for a polymer sample. Remember, here we are telling the temperature at which polymer undergoes crystallization and cooling, because on heating sometimes there could be a crystallization, heating induced crystallization, and that will also induce crystallinity, but that is not a melting temperature, that is called Tc or crystallization temperature, which is not a true transition in per se. It basically, when we heat a amorphous sample, sometimes if the polymer structures are basically conducive, they can actually form crystal domains. So, we at a particular temperature which we call Tc or crystallization temperature. We will come back to glass transition temperature. This is the temperature at which the glassy state is changed to a rubbery state or vice versa. The glassy state is a short range in glassy state we have short range vibrational rotational motions of atoms, and which is a hard, rigid and brittle state. Whereas, rubbery state we have a long range rotational motions of the segments about 20 to 50 atoms, and it is soft and flexible. Now, when you heat through Tg, there are breakdowns of van der Waals forces, onset of large scale molecular motion in polymer molecules. Polymer goes from glassy, rigid to rubbery behavior, and for a perfectly amorphous or a completely amorphous material, this is very important because that gives the upper surface temperature in amorphous polymers. So, basically if you talk about PMMA, polymethyl methacrylate, which is having Tg of 105 degrees centigrade, then that is the highest temperature. In fact, the temperature is little lower, that is the usable temperature for a PMMA, or for polystyrene if the Tg is 100 degree. So, the highest useful temperature is probably 90 degree or 90 and so on. So, basically that is the upper surface temperature in amorphous polymer. So, the ability to form glasses is not confined to non-crystallization stable polymer. So, when you talk about glass transition temperature, it is not only restricted to polymers. There are other examples where glass formation takes place, like the glass we typically, like silica glass we typically use in our household items. They are not polymeric, but they are semi ceramic glasses, and so basically any material that can be cooled sufficiently below its melting temperature without crystallizing will undergo a glass transition temperature eventually. Above the glass transition temperature, if the polymer is amorphous and linear, it will flow, but have a high viscosity. But if a polymer is crystalline, means partly crystalline, then melting temperature is always above the glass transition temperature of that particular polymer. So, if we have a semi crystalline polymer, I have a Tg which is lower than the Tm, and my upper surface temperature would be the Tm in this particular case. We continue our discussion on amorphous state or glassy state, and in this case the polymer sample consists of long chain polymer molecules entangled with each other like a liquid like manner. There is no order, no long range order in this case, but with a complete absence of rapid molecular motion, which is typical of a liquid. In case of liquid, we know the molecules are always moving and you have a particular velocity along with associated with those molecules. But in case of polymer glass or amorphous glass, there is no long range ordering like a typical liquid, but there is no motion of or the more molecular rapid motion in this case of polymer glass. So, there is a difference between a typical liquid and a polymer glass. So, in true sense polymer glass is probably more alike like a liquid state, but because it has no molecular motion and the viscosity is completely high. So, practically in practical point of view, it is actually a solid material from a practical point of view, but in a molecular point of view it is a liquid material. So, it has immobile molecular backbones which are frozen in entangled conformation, does not exist or exhibit a crystalline X-ray diffraction peak, it only shows a diffuse ring. So, unlike a crystalline material which gives a discrete ring and gives a crystalline X-ray diffraction pattern, amorphous material do not give those discrete ring, it gives just only diffuse ring. As I said, in older literature, these are often referred to as amorphous state is often referred to as liquid state, but at present the polymers in a glassy state are better called amorphous solid. Small angle, this is very important, small angle neutral scattering has been used to show that for a pure amorphous polymer, the polymer molecules adopt their unperturbed dimension. We talked about different dimensions like end to end distance in different with increasing restriction, and we talked about unperturbed dimension there. So, basically which happens for polymers in theta solvent, if you recall. So, for pure amorphous polymers, the size of a polymer will resemble with a unperturbed dimension like the dimension in a theta solvent. Now, the glass tension phenomena is also described from a free volume theory. Now, free volume is the space in a solid or a liquid sample that is not occupied by the polymer molecules, or is the empty space between the molecules. And in liquid state, obviously the free volume is high, which enables easy molecular motion, and with decrease in temperature, most of the thermal contraction of the polymer rubber or melt can be accounted by a decrease in the free volume. So, with decrease in the temperature, the free volume actually decreases, and as a result the volume of the sample decreases, which basically cause the thermal contraction. So, if we plot a volume of a polymer sample with say temperature, if we plot temperature here and volume of the sample, and this is V0, which is basically the volume of the polymers, the polymer molecules, which is slightly dependent on the temperature. As the temperature increases, volume goes up, but the total volume, if you think about total volume, then this is the total volume, and as we decrease the temperature, the total volume decreases quite sharply in molten state, and below the glass transition temperature, there is no further contraction possible as we discussed because of the frozen molecular motion. Hence, this total volume remains almost same. Now, this difference between the actual volume and the volume of the polymer molecules are termed as free volume. This is called free volume. So, the free volume after or below the Tg remains almost same. So, the value of free volume below this Tg, this value is almost constant no matter what is the temperature, whereas above Tg the free volume increases with temperature. So, with decreasing in temperature, most of the thermal contraction of the polymer rubber melt can be accounted by decrease in free volume. Eventually, at some temperature which is Tg, there will be not be enough free volume. There will be not enough free volume for the molecules to reorient or change the conformation for further compaction. So, if the polymer molecules want to further contract, it requires some space to rearrange themselves. If that space is not enough, if there is already entangled, there is no space, obviously it cannot further compact. Although thermodynamically it wants to compact, but because there is no free space available, it cannot contract. So, this is Tg. So, basically eventually at some temperature Tg, there will be not enough free volume to allow molecular motions to take place for further reduction in free volume. So, total volume is given by the volume of the polymer molecules plus the free volume, and the fraction of free volume is given by the free volume divided by total volume, and this is the free volume below Tg. So, this value is, this difference in volume is Vf star, the free volume below glass transition temperature. So, the total free volume is given by this free volume plus change in temperature and the rate of change of volume with temperature. Rate of change of volume, because this does not change much, the fraction of free volume is given by free volume before or below the glass transition temperature, and the thermal, if we divide by A volume both the sides, we get this expression. So, 1 by V dV by dt will be given by thermal coefficient expansion of free volume or coefficient of thermal expansion of free volume. So, alpha F is the expansion coefficient or coefficient of thermal expansion of free volume. Now, looking at the polymer structure, we can actually find out there are different factors which influence the value of Tg. As intuitively you can guess, if the backbone structure is more stiff, obviously the mobility or the rearrange the capacity or the tendency to rearrange themselves will be lower, hence the Tg will be higher. If the steric effect is higher, which means again the probability of rotation around the single bond will come down, Tg will be higher. If the intermolecular force is higher, obviously again the chains will not be able to rotate more freely, the Tg will be higher. Similarly, the factors which increase the free volume, like by reduce the molecular weight, adding a plasticizer molecule or a long chain side groups, they actually increases the or influence the free volume. So, basically they influence the value of Tg. So, if you increase the rigid group in the backbone, then Tg goes up. If you increase the flexibility, then Tg goes down. If you increase the steric hindrance, Tg goes up. If you increase the polar functionalities, then Tg goes up. If you increase the cross linking, obviously the mobility will come down, Tg will go up. Similarly, in terms of free volume, if we add plasticizer which will increase the free volume, Tg will go down, and if we have a long plasticizing side groups, then also Tg will come down. We will give some examples, comparative examples to show these trends, but you must also remember that it is not always that single factor which is in effect. Like if you have different side groups, they may actually increase the steric hindrance, but decrease the polar interaction. So, what I want to say that it is very difficult to completely account for the Tg values by only one factor. There could be multiple factor which is actually finally responsible for the Tg value of the polymers. For example, if we talk about this, compare the Tg value of these three polymers, then this is silicon oxygen bond is very flexible, even flexible than its carbon carbon bonds. Similarly, if we have aromatic background, obviously the flexibility is much lower or the stiffness is much higher, hence the Tg, as you can expect, this will be much higher for this. So, if we give the values, so this will be minus 120 and this will be this polyethylene, this has the Tg is not a fixed like minus 80 as I mentioned here. This is a representative value. The Tg of polyethylene actually depends on various parameters like the molecular weight, crystallinity, branching and so on, but it is having quite low Tg and it has actually a range of Tg. So, it can from minus 100 or minus 120 to even go around plus just less than 0 degree and so on. As you can see that the stiffness of the backbone increases, the Tg goes up. Similarly, if we compare these three polymers, as if you introduce a carbon oxygen bond, this flexibility goes up, hence the Tg will expectedly go down, and if we increase the aromatic group in the backbone, Tg is expected to go down as the stiffness will go up. So, if we compare this value, as you can see, this minus 80 is minus 60. This example this might increase the flexibility, but because of the intermolecular interaction is higher, presence of polar group, the Tg is actually little higher in this particular case. As I was saying that there could be multiple factors which determine the value of Tg, and in case because of the stiffness is higher, the Tg is much higher compared to these two polymers. If you compare the Tg of these 4, as you can see, if you increase these CH2 groups, then the flexibility will be higher. When we have this aromatic group, flexibility or stiffness will be high, flexibility lower, stiffness will be higher. As you can see, this Tg value comes down, but because of the aromatic groups in the backbone, the Tg is drastically higher. In this case, if you carefully look that as we increase the CH2 groups, actually number of polar groups is decreasing. So, in fact, in these cases the intermolecular forces actually decreases, which should also account for the decrease in this Tg value for this sample. Similarly, if you compare these two, obviously this is much stiffer, it will should have a much higher Tg value compared to this polymer. When you compare the steric effect of the side group, you can see that as we increase the size or bulkiness of the side group, the steric effect increases and the rotation around this single bond becomes more difficult and stiffness increases. As a result, Tg goes up as we increase the steric size of the side group. Similarly, if we have polar groups, obviously intermolecular interaction goes up between polymer chain, as a result Tg goes up. If we compare these two, you can see this is a higher temperature, higher Tg, and if you compare these three, then obviously presence of chlorine will increase the intermolecular interaction. As a result, Tg will go up as it is seen here. Intermolecular interaction compared to a hydrogen and methyl group will have a higher intermolecular interaction because of higher van der Waals forces between the polymer chains. As a result, you have higher Tg. This will also increase the steric hindrance, that will also contribute to increase in the value of this Tg value of this polymer. If you compare these three cases, then as we increase the polar substitution, in this case the steric effect are almost similar. So, the intermolecular forces or the polar effect will be mostly detrimental for value of Tg. If you look at this value, the higher is the polarity, higher is the value for Tg for these polymers. Now, this is for the contribution from the free plasticizing groups or increasing the free volume. In this case, methacrylates, if we increase the size of this R group, and now once you increase the size of the R group, this becomes more flexible, and as a result the free volume increases, and as the free volume increases, the Tg comes down, because as the free volume, as I explained, that the free volume increases, it has more chance or more space to rearrange itself at a particular temperature. So, it can go down, the Tg can go down further. So, if you compare these values, methyl, ethyl, propyl, butyl, you can see as we increase the chain length, the Tg value decreases steadily. When you increase the size of the side group, like if you compare a N propyl and a isopropyl group, because this is a linear chain and this is a more of a bulkier group, this will have higher Tg. Similarly, from a normal propyl to a propyl group, you have a higher Tg. Similarly, compared to a normal butyl to a tertiary butyl, you have a much higher Tg. So, which means that long linear side chains actually increase the flexibility and decrease the increase the free volume. As a result, the Tg goes down. If we add small molecules which are miscible, which dissolve in the polymer matrix, it actually decrease the Tg quite significantly, and that is used for aiding polymer processing process. If the polymer Tg is higher, then these plasticizers are added to decrease the Tg for helping in processing, and that happens because on dissolving small molecules, the free volume increases. Whenever there is requirement of very high heat stable polymers, as you can see, these are amides or imides which are very aromatic groups in the background. So, in this case it has very high intermolecular forces and very high rigidity or stiffness in the backbone. As a result, you can see the Tg values are very high, and these polymers are used in a very high challenging environment where heat resistant polymer, requirement of very heat resistant polymers are very high, like in space applications or where the friction is very high, the polymers need to sustain that particular heat. There are some other observations about Tg values, but there is no generalization. For example, unsymmetrical substitution have higher values, for example, this has a higher value than this, and so on. So, these are some of the values you need to remember, or if required you need to find out from literature. There is no particular trend. Similarly, the glass transition temperature dyeing polymers also is not very predictive in terms of cis and trans, and tacticity also actually change the Tg value. Basically, if we have a more ordered structure, then packing becomes easier, or and as a result the Tg value should be lower compared to a where Tg value should be higher compared to a situation where there is no basically no particular order of tacticity. For example, isotactic PMA, it is having much lower Tg value compared to a syn dialectic. In fact, these are it is predicting or explaining this tacticity driven glass transition temperature is quite complex. Hence, it is better to remember the values, or at least you should understand or you should appreciate that if we change the tacticity of a polymer, there is a possibility of changing the Tg value as well. So, we need to determine the Tg value before we think about a application. Now, there is a significant effect of molecular weight on Tg. Now, Tg of basically it is given by this expression, and I have shown these values. You can actually look at the meaning of these parameters, like this is the value for Tg of polymer having infinite molecular weight, this rho is the density of polymer, y is the number of chains per polymer chain, and so on. Mn is the number average molecular weight. Hence, it basically as the molecular weight increases, the Tg value approaches close to a limiting value, which is for a having infinite molecular weight. So, as molecular weight increases, Tg increases, but this increase becomes less important or less significant as we go beyond some particular value of molecular weight. For high molecular weight beyond a particular Mn, practically the value of Tg remain unchanged, and as branching increases, Tg decreases. As we understand, if we have more branches, then free volume increases, Tg decreases. So, effectively this difference with the Tg of infinite molecular weight with the particular Tg is inversely proportional to molecular weight. So, as the molecular weight increases, we approach a limiting value of the Tg, which is a infinite molecular weight. So, if we plot like in this case, it is shown for PDMS, polydimethyl siloxane and polystyrene. This is a Tg value in Kelvin, Tg in Kelvin, and this is Mn. So, as you can see that as we increases the molecular weight, Tg goes up, and after beyond a certain molecular weight, it actually levels off. There is no practically there is no change in Tg value. So, if we want to, and this is you can see that this value is about say 8,000, 9,000, 5,000, in this case about 10,000, and in all practical purposes we deal with the molecular weight above this limiting or this molecular weight. Hence, when we use for practical purposes the molecular weight range what we typically use, they are almost independent of the Tg value is independent of molecular weight in that particular range. If we go below a certain molecular weight like oligomeric range or low molecular weight, then Tg actually becomes affected, becomes lower and lower. So, with this I will stop today for these amorphous polymers. Next I will talk about crystalline state in next class.